Hello everybody, welcome everyone aboard. We are here yet again on May 2013 live webinar, and today's we are proud to present the new topic: how to be sure that your robot's design is suitable to manufacture. We have our industry expert along with us, who is here to share his experience and take his valuable time out of his busy schedule and share his experience with all students. And he's an industry expert in Adams. So if we speak more about him, it will be not good because it will steal away time from the industry expert. So over to Pankaj. Pankaj, you can start now. Thank you.
Thank you, Manish. Thank you, ROBOCONHELP, and welcome all of you. First of all, good evening, and welcome to this webinar. Our topic today is how to be sure that your robot design is suitable to manufacture. My name is Pankaj Pawar. I work for a company that produce off-road vehicles. We generally analyze those vehicles on dynamic basis, like how the stuff is going to work in the real actual field, and how the performance of the vehicle would be. So those vehicles can be construction and forestry, that can be heavy tractor, that can be a big combine, a mining truck, or any suitable off-road vehicle you can think we generally analyze them. So I'll quickly forward to agenda. So first of all, introduction. In my introduction is I am a graduate from IIT Delhi. Even though I have attended my classes with Manish Chauhan, and I have been working in this industry from last 3 years, and I have been active in robotics and robot seminars from last 3 years, or maybe on personal level, professional level, and I get a chance today also, to present this thing in front of you. So today we'll be talking a little bit on the basics, while we analyze few things, what can be, basic term we use, and what will be the basic things that we have to keep in mind all the time. Then we'll be talking about major tools that can help us to evaluate our products. Then we'll be having a little tutorial on how we can start modeling the thing in one of the tools, and then we'll take a case study on SCARA robot, and then we'll find out what was the learning and outcome of this thing webinar. So before we I'll talk about basic. I want to make it sure why we are doing this. Why we need to evaluate or check the performance of our concepts before the manufacturing. So the first thing comes to my mind is that a valid design? Is that the right link lengths I'm using? Am I using the right torque producing motors? Is my control system is going to work in the real scenario? What will be my size constraints? What will be my other requirements, say cameras, say semiconductors, say different mechanism, or will it be the outcome, will it produce the same functionality as I want? So these questions can be answered by using some of the tools available in the market. We can virtually analyze them. We can evaluate them before the actual manufacturing. If we follow this kind of procedure, it will give us more assurity, more confidence that okay, this thing is going to be successful on higher rates. So the probability of success will be higher. So I'll now take on the basics. So I guess everybody knows what is link, but let's say each resistant body in a machine which moves relative to another resistant body is called link or element. Link can be of any size, any shape, and any dimension. It can be anything. If we see around us, anything moving, any part of it, a boom of a construction forestry machine is a link. So if you look at a serial manipulator, or you see a 4-bar, there are links. If you look at some lathe machine, there are links. If you look at any other machine available, a car, a steering mechanism, there are so many links. So then we'll move to the joints. A connection between 2 points called joint. So it's basically when we have 2 links, we have to connect them in a manner that it will produce the required movement. So say if I want a oscillation, I should have a revolute joint between 2 bodies. If I need a full rotation in all 3 directions, I have to define a spherical joint. If I have to take a linear motion, I have to define a translatory joint. Then the other thing comes in mind is motion. A forcible action which make one thing to move is motion. In motion, there can be 2 basic motion. One can be angular motion, another can be linear motion. So for angular motion, we can give angular displacement, angular velocities, angular acceleration as our input, and then we can give linear motion, linear displacement, linear velocity, and linear acceleration for the linear motion. So where we need angular motion and where we'll need the linear motion. So say if we have a 3 degree of freedom SCARA robot, we should have 2 angular motion and 1 linear motion. I'll talk about it on detail when we'll be talking about SCARA. So what is mechanism? So a combination of joints and links is a mechanism. So mechanism can be a 4-bar, very simple one, simple machine like your plier, engine. It has a translatory and rotatory motions and links. So then we can have serial robots. So if you see over here, we have a spy robot which has a camera installed here. If I remove this platform and wheels, it will be a serial robot. Then we can have training simulators like training for army soldiers, simulator for your car driving, simulator for your flight, simulations. Then we can have mobile bots. So basically any robot moving with wheels is a mobile bot. Then robot. So every robot is kind of machine, but every machine is not a robot. A smart machine which can understand and behave as per command will be a robot. So command can be of 2 types. So a fully automatic or autonomous robots, or the robots which require a human interaction time to time. So say if I have a construction machine, you might have seen a yellow machine all around us, digging up the soil and throwing it somewhere else. So it's also a robot, but it requires human interaction time to time. So driver will be giving it a command time to time. Then we'll move a little bit further. Tools. There are several tools available in the market which can help us to evaluate our product, its efficiency, its manufacturability, its reliability, some question on the vibration, if there is a lot of vibration coming on, or its strength, or maybe to evaluate the motor ratings. So these are the major tools available in the markets that we use day-to-day life. It's Adams, Autodesk Inventor, and LMS Virtual Lab. We'll be having a tutorial on Adams, which is a product of MSC Software. and it's a major tool that automobile industries and the dynamic base industry use a lot. Now I'll move to one of the tutorial. You know, I'll be giving you one example like how this stuff works. So I guess everybody can see my screen. I have this tool open. So basically this kind of tool provide us so many functionality, like I can create few simple links by using some command like simple link, box, then cylinder, then spherical things, then trapezoidal thing, then you can do a little bit extrusion points, then polyline and other construction material. So what I'll do, I'll quickly make a rigid link. I'll say, okay, this link should be acting from here to here. So this is basically I have defined the length of this link. Then this software also provides us some joint types. So we can have these type of joints. So say revolute joint, universal joint, fixed joint, translatory joints, spherical joints, cylindrical. I'll say, okay, this one is a very simple one, simple mechanism. It has a revolute with ground at this point. So this is very simple mechanism. I'll say it is a pendulum hanging on hanging with the wall, and I'll say, okay, now I have to give it a motion. I'll say, okay, give it a rotatory motion about particular joint, and I'll say, okay, my control system is such like that it produce a sine wave. So I'll say, okay, it's a sine wave of magnitude 60 degrees, and this sine is directly dependent of time. I'll say it's a velocity. I'll say, okay. Manish cannot. Okay, so now I'll say, okay, can you solve it for me? I'll say, okay, I'll make it a little bit slow. Okay, I'll run it. I'm sorry, Manish, I thought we got disconnected. Thank you for that. So that's how I can model one thing, and I'll say, okay, I had this one motor. It has some control design, and it has one link. I'll say, okay, what should be my motor's requirement? So I'll say, okay, go to this screen. I'll say I have one joint which has one motor over here. I'll say element torque. I'll say magnitude. I'll say add it. So can you see that we had this mechanism which was moving in this fashion, and it has several vibration coming in out. So the reason was we have gravity continuously acting towards the ground, which compels, try to fix this mechanism always towards the ground. So we'll quickly go back. Now I want to say, okay, let's make it a little more complex. I have one more link, and this link is being connected with another link with respect to another. Okay, say one link, part 3. I'll say part 2. I'll say, okay, and I'll say, can I run it again? Oops, I'm sorry, that's my bad. So I'll say mosh. To modify. I'll say part 2. Okay. Now I'll solve it again. So that's how, if I have two links and a joint defined between two, that's how they are going to move in the real conditions. So it's kind of a validation of a 2-bar mechanism which is hanging with the roof. So that's how we can simply validate the things. Okay, the stuff is going to move like that. It will be the output of that. That will be this will be the point. Will be moving around and it may go crazy sometime. So that's how we can evaluate. Okay. So I'll move back to my presentation. So now we'll talk about more on SCADA robot. SCADA is a widely used industrial robot. It's been widely used in assembly processes. So the assembly process of semiconductor PCBs, almost every PCB making manufacturing facility does have SCADA robot most of the time. So let me explain a little bit more on how this stuff works. So this column always remain fixed with the ground. This link has a connecting joint between the base and this link over here. So it can have a rotation of full 360 around here. Then we have another link over here which is connected to first link over here in this location, and it has another 360 of degree of rotation. Then we have last link which can translate over here, and it has a translatory joint. And this model you see over here is the advanced model that I have already created for you guys, and I'll be telling you what kind of control I'm giving it to. So before we go to learning, I'll again go to my application on atoms. So I guess you guys can see this SCADA robot. So say this is my concept. I know there will be 3 moving links. I have little idea like it will be having revolute and translations. Now I do not know what can be my torque requirements, what can be the motor size, what can be the physical limit of this concept. Will it go crazy at some time? So that kind of stuff I really do not know. So what I'll do, I'll go to this capture. I'll start creating few things, start applying joints and few motion. So say I have this joint between orange and the green link, and then I have defined, okay, there should be one motor, and I'll say, okay, that this is how my control system should work. So it should rotate 360 degrees. Then it should have a sine wave based on 3 times, so 3 times to the time, and I'll say it's a pure displacement. Then over here I'll say, okay, I have another motion. I'll say, okay, for timing this motor is there, but it's not giving any input. It's a kind of steady. It's producing 0 output. And then I'll have this linear motion here, which is another kind of motor. I'll say, okay, this motor can have minus 100 mm, sorry, of sine 10 into times. Then I'll say, okay, how this stuff is going to work. And I'll say, okay, can I simulate it? I'll say, okay, move it by this amount, and over here. It may take few seconds to solve. So I'm going to run the animation or for this robot that I have just solved, and it may be a little jumpy for you guys because we are on on remote presentation, but I'll try to help it out by making it a little bit slow. So I'll say, okay, marker should be traced here. I want to see how this tip of this red link is going to behave and how it's moving around. So I'll say, okay, run it. Manish, can you hear me now? Manish?
Yes, Pankaj, we can hear you.
Okay, thank you. Sorry about that, guys. I got disconnected somehow, and I really apologize for that. So I'll quickly take up on, when I have this concept in this tool, so now I would like to analyze it kinematically. So kinematically means is it going to do the same functionality as I want? Then I would like to check upon the dynamics. Is it going to behave good? Is it going to behave random? Or is it going to behave with some vibrations? So that is all about the dynamics. Then I want to check on my control system. I'll say, okay, my semiconductor would produce so and so output. Will in with that output, how this system is going to behave. Then I'll check my shape and sizes. So this one, if you're looking at these links, they are very simple in design, and it's basically uh, most of the time rectangles or cylinders. But you can have better design. Maybe you can create something in Pro-E or SolidWorks, then you can import it over here. So sometimes we
Um,
have size constraints. Hello.
uh, Pankaj, sorry to interrupt, but your screen is not showing up. So could you please show up your screen?
I'm showing it on my application, and my application should be okay. So Manish, can you see the SCARA robot now?
No, I am not.
Can you see it now?
I was just able to see and then it just suddenly disappeared.
Now?
No. Yes. Yes.
Oh, okay. Sorry about that. I am using this thing very first time. I guess I am making mistakes in here. So those are the 4 points, and then fifth point can be my size constraints. Like if I have to make a spider bot, it should be very small. It should pass through certain passages. If I had to make a material handling robot, it should lift up to 11 feet. If I'm making a mobile robot, it should not have too much mass. It should be very light. A marker, which is basically the endpoint of this rotating body, and it's tracing this path, and it's showing like if you are going this particular control, these particular joints, these particular length of links, that's how I'm gonna behave. So we can play a little bit, but I'm afraid last time we got disconnected because of making changes to this thing. I'll give it another try, but I don't really want to mess it up. I'll say, okay, I have a little more motion on second link also. I'll say it should have a sine wave of 5 times of time. I'll say okay, and this time I'll run it very fast because it may hang up. Alright, thank God it didn't. Oops, it was very fast. I'll say okay, I don't want that fast. Can you generate it for just 1 second? And it should have 5,000 times. Okay, I'll say okay. Say yeah. So can you see that it's making like some circular shapes, and it's going, sometime it's going very fast. So see, if I have this thing already evaluated over here as compared to manufactured one, it's very easy for us to iterate it. It's very easy for us to evaluate the mechanical model, the control model, the shapes, the sizes. It's very simple. I had to change few numbers, and here it is. You can have everything. So I'll show you this video once again with different angle, so that you can have little more understanding. Say okay. I'm really sorry if if these videos are coming up to you very jumpy, but I'm trying to make it very slow, and it may not help that much. So here one thing we have noticed, like the blue link is passing continuously through the orange link. So it means we have to design our control system. We have to design our mechanical system in such a way that you should know, the mechanism should know its physical boundaries. It shouldn't pass through, or it shouldn't strike to the other links. So that is a basic need of today's industry, to be more efficient, more reliable, and cut on the our manufacturing cost. So it's that's how we evaluate our system before we go for manufacturing, and it saves a lot of time for us. It saves lots of money for us, and it's also tell us either this concept is validate or not. Is it going to real work? Is it really it's a good design, or it's it requires some area to be improved. So guys, this was all about SCARA robot. I'll show you my presentation once again. Let's say, right. So what are we are learning today? So we have learned about kinematic validation. Means, is it our robot going to serve the same functionality as we want? Is it going to do the same work as we want? Is it going somewhere else? Is it going crazy sometime? If it's yes, you are good to go. Then I'll check on the dynamic scope. Is it going? Is there any lots of vibrations? Is there lots of forces generating around? Is it showing any sudden fall or sudden jumps? And then we can see our control system. I have shown you like how we can change some sine waves. That was not a real output of a control system, but you can have little more sophisticated control system design over there. You can define input as your suppline. Suppline means you can have a certain range of points that your robot should follow these particular points when it was moving. If you are good with control system, give it a yes. Then you can check on the motor ratings. Is it going to we can check if the at certain motor location are we getting that much torque, and is my motor is available capable to generate that much torque. So if your motor is capable of that, or you may choose a certain motor, you can have you can check on catalogs, and you can decide one good motor for that. Then you will say yes. Then I'll say is it workspace of the robot is good enough, or we need to widen it up, or we need a lesser workspace, the external limits of the robot. So you can check on that if it's good, if yes. So if we have yes on all of 4 or 5 points, we'll say, okay, this prototype is good to be manufactured, and it's gonna be a good deal, not a great deal. Maybe there are still something that we have not seen, but it's still the probability will be very, very high as compared to just the conceptual design is going to directly to manufacturing. So it will be giving you more reliable product at the end. So that's all I had about how to test your robot before manufacturing, how to validate your concepts. And if you have questions, please ask. And this is our products on RoboConHelp that you can buy, that you can ask for, that you can think to put as a one of the part of your robot. And feel free to contact us. This is our email ID, and I'm very thankful to Manish and RoboConHelp to give me this opportunity to present in front of you guys. If you have any question, I'll hand it over to Manish.
Yeah, thank you, Pankaj. There is one question coming from one of our listeners. He says that can we put control systems on Adams?
Yes, it's possible. I'll give it 2 options in that. I can suggest 2 options. One of the thing is I can simply define a control system here. So basically a control system can be defined with respect to some mathematical functions. So we have sine, cos, we have Fourier cosines. So there are a lot of things available in Adams itself that you can model your equation of motions. Then other than that, I can put sublines. I can take a test data. I can attach Adams with another control software. So say if you are working in LabVIEW, you can connect Adams directly to the LabVIEW. So say you have a control system, simply a PCB sitting in the LabVIEW, and you can say LabVIEW will be giving the instruction to Adams model, and it can evaluate your model as per the LabVIEW's commands. So yeah, there's another tools available for that. Easy5 is there. Then there are another tool like ME-SIM is there that can you can for highly sophisticated control design you can choose other product. Otherwise, it's I guess for student level it's perfectly fine if you are using Adams.
I mean to say that.
So the answer is entirely say yes, we can do that.
So it means that all the PID and PD controls can also be incorporated with Adams?
Yes, it's possible, but it's possible. It's you have to design your PIDs. Then you can say, okay, I have this much error coming in the model, and I have to integrate in such fashion. I have to differentiate in such fashion, and then you can make it like that. It's possible. You have to use these functions. There are so many functions available here. So with help of this function, you can create PID controllers or any other controller you want to do.
Thank you, Pankaj. There's one last question coming from one of our listeners. He says that how can we learn Adams? Do you have any tutorials available by which we can learn Adams?
Yes, for Adams, there's lots of tutorial available in online, and there's a MSc Software's website which will provide you a little help on that, but you require it has some entry-level fees for that. But yeah, of course, a lot of materials available online that you can use to learn Adams. And other than that, if you need some help from Robocon, we are here. We can support you in that fashion. We can provide you online help like this webinar. You just feel free to ask. Even I do sometimes provide this professional help and learning atoms and basic fundamental to advanced approach in atoms. So feel free to ask. We can take it offline. We can you can discuss it with Manish. It's available. It's very easy to learn anyway.
Thank you so much, Pankaj. It was pleasure having
Manish,
you
is
at.
that answer?
Yeah, thank you so much, Pankaj. Your answer was completely satisfying. And we thank you so much for coming online, and really apologize our audience that it just messed up twice in between because of some internet mishaps. The recorded version will be there online so that everybody can have benefit. Uh, and it, once more, we just give heartiest congratulations to Mr. Pankaj Pawar for taking out his valuable time and presenting this webinar. Thank you so much. Thank you, audience, and thank you, Pankaj, once again. Thank you so much.
Yeah, thank you guys. Thank you very much for your patience, and I apologize for disconnecting several times. Have a great day. Thank you.